All right, so we are in section 9.4. 9.4. So we're going to talk about parametric equations. We have used parametric equations in the class before. We just didn't call them parametric equations. So one example would be, and you probably use them in your science classes, when you talk about projectile motion. So you have x, you have your x coordinate as some function of t. So distance equals function of time, and we also have an equation that gives our height as a function of time. So we're plugging in time into these two different equations, and one tells us how far left or right we've gone, and the other tells us how far up and down we've gone. So this would be an example of a set of parametric equations. And the contrast to, we'll call our normal, I'm going to put that in quotes, our normal equation. Normal equation, I call them the rectangular equation, the ones that we usually work with, where we get y equals some f of x, where we plug in an x value and we get a y value out. In parametric equations, we're plugging in a parameter. Here our parameter is time, and we get an x and a y out. So just to contrast those two a little bit. So we're going to talk about a little bit of terminology, and then we'll talk about how we work with these parametric equations. So what we have is x, I'm going to write it out like this, x equals, for parametric equations, x is some function of, we're going to call our parameter t here, but our parameter doesn't always have to be time, it's just some number. So parametric equations, x is some function of t, and I'm going to write x of t, that tells us it depends on our parameter, and y equals y of t, so x and y both vary with our parameter t. If we make ordered pairs of these x's and y's, so we make ordered pairs over some interval, so we're plugging in for our parameter t equals 0 to t equals 10. Ordered pairs, and we get an x value for each value of our parameter t and a y value. We call that set of ordered pairs a plane curve. This is how we draw a sketch of our parametric equations. And they call that sketch for parametric equations the plane curve. And t is the parameter. Often we think of our parameter as time, but our parameter doesn't always have to be time. Our parameter could be lots of different things. We're going to, when we start talking about polar coordinates, our parameter is going to be an angle. So we'll plug in a theta value, and that will give us a point on the plane. But we can use lots of different things as our parameter. One reason that we write equations in parametric form is that it allows us to work with the equations in just a little bit different way. Sometimes it's easier to work with a set of parametric equations than it is to work with y equals f of x. It allows us to do certain things. And what we're going to do eventually is write our conic sections in parametric form, and that will allow us just to work with them in a little different way. Parametric equations are very important as you move on in math, so they're not something that you do something a little bit with and then it never shows up again. Just today in Calc 3, we were using parametric equations to work with the topic that we're working on. We're going to use parametric equations basically for the entire rest of the year in Calc 3. So they are something that does come back that you do end up using a lot. It's a very useful tool to be able to write your functions in parametric form. So what I want to do is we'll talk about how we're going to graph parametric equations and some special things that happen with parametric equations. We're just going to work with them a little bit today. So sketching, we want to sketch a plane curve. So the most basic way is we're going to make a table of values and plot points. So let's say we have our parametric equations. X equals 2t and y equals t squared plus 1. So this is our set of parametric equations, and we want to sketch on the interval -2 to 5. And remember, this is saying -2 less than or equal to t, less than or equal to 5. So we're only sketching the curve for a certain range of t values. So the most basic way that we can do this is plot points. So I'm going to make a table for t, x, and y. And we're just going to go count by ones from -2 to 5. So I'm going to do -2, -1, 0, 1, 2, and then I'm going to go, we'll skip a couple here and go to 5. So to find our x and our y, I just plug this in. When t equals -2, x equals -4, and y equals -2 squared plus 1 gives me 5. So here's going to be our graph. All right, so my first point is at -4 and up 1, 2, 3, 4, 5. There's my first point. When t equals -1, x equals -2, and y equals 2. So -2, 2. When t equals 0, x equals 0, and y equals 1. So I'm going along my curve here, so I get this nice curve like so. And notice that we're traveling as t gets bigger. As t is increasing, I'm traveling on my curve from left to right. And we'll talk about that in just a second. When t equals 1, x equals 2, and y equals 2. So there's a point 2, 2, so we go up along like so. And when t equals 2, x equals 4, and y equals 5, so I go over 4, 1, 2, 3, 4, and up 5, so I'm back up at this point. So I end up with a nice parabola shape. And then finally, at the end of my interval here, when t equals 5, x equals 10, and y equals 26. So at my point way out here, I'd have a point at 10, and way up here at 26. So I'd end up with a point way up here. And at the end of my graph, I'd look something like that. So this would be my plane curve. for this set of parametric equations on the interval t equals -2 to t equals 5. So a couple of things about plane curves and parametric equations. Parametric equations always give us an orientation. We always travel a specific direction along the curve as t increases. And that direction is not always left to right. If we have y equals f of x is always getting bigger. We always go from left to right with x. Well, depending on how we parameterize our curve, we could travel from left to right or right to left. So we always end up with an orientation. So our orientation here is saying which direction do you travel on the curve as your parameter gets bigger. Our orientation here is left to right. Doesn't always happen to be left to right. Our parameterization is not unique. We could come up with a different description of this curve with a different set of parametric equations. So this isn't the only way we could represent this parabola with parametric equations. There are several different ways that we could do that. And we'll talk about different ways of parameterizing a curve in a little bit. But parametric equations aren't unique. We could come up with different ways to describe this with different sets of parametric equations. So this is one way that we sketch a plane curve. Table of values. We always end up with an orientation. We could always represent that curve in multiple ways. Let's take a look at how we use our calculator. Our calculator is nice. It will let us sketch parametric equations. I forgot some letters here, didn't I? Sketching. That looks a little better. All right. Let's look at another example. This time we'll do it in our calculator. So let's say we want to sketch x equals t squared and y equals t minus 1. And our interval is on -3 to 3. So this is telling us -3 less than or equal to t, less than or equal to 3. So in our calculator, we're going to go into we're going to hit the mode button. And down here where it says function, we're going to go over here and highlight parametric. And hit enter. You want to go here in your mode, go down to function, and then arrow over to parametric. And then we're going to hit enter. Quit out of there. And now when I go to the y equals menu, rather than just a y1, y2, y3, I have an x1 and a y1. So that's our set of parametric equations. So in x1, we're going to put in t squared. And then in y1, we're going to put t minus 1. And then we want to sketch that from -3 to 3. So I'm going to go to my window. And I'm going to put for t minimum, -3. And t maximum, 3. And this t step just tells us how often we're plotting a point. So every 0.13 for t is increasing by 0.13 each time. And we'll go, yeah, this looks fine here. It's probably fine however it is set in your window, as long as these numbers aren't really big. And then we hit graph. And there's my graph. And you notice as it drew the graph, it went along here and then back that way. So as t increased, the graph was sketched that direction. So our orientation would be we draw little arrows on the graph showing that we traced it along that direction. So there's a graph of our set of the plane curve for our set of parametric equations. So we were able to graph this sideways parabola using parametric equations. So let's go back here. So our graph, just to sketch a quick graph, ended up looking like this. and our orientation, we traced along the graph this direction as t increased. A couple of interesting things about our plane curves, about graphs when we graph parametric equations. T doesn't show up on the graph. This is my x-axis, this is my y-axis. T just gets us, for every value of t, I get a new point. So t doesn't show up anywhere on the graph. So if we had something, a particle, an object that was moving, that was described by these parametric equations, and we said t is time, this would be the motion that it would describe as time increased. Start here and go around to here. But t, our parameter, doesn't show up on our graph. And our units on our graph on the calculator, so what I wanted to go to the calculator, these x changes by 1. Well, t, just because x is changing by 1, t is not necessarily changing by 1 there. If x changes by 1, x is t squared. So it really depends on how we set up our parametric equations, how x and t are related, or how y and t are related. T, you have to get used to the idea of t not showing up on the graph. All right, are we good with that example? Let's look at another one. Let's look at x equals t cubed and y equals t squared. And this is, let's go from -5 to 5. So in the calculator, we'll go back to our y equals, clear that out. I'm going to do t cubed. Clear that one out. We want that one to be t squared. For our window, I'm going to go from -5 to 5. And this will be, our window I think should be fine. I think that, let's see, I think this is going to have to be a little bigger, so let's do the y minimum. I'm going to do a 0, and I'm going to go to 25. And we graph that. Now, let me adjust my window again. There we go. So there's a graph. There's a graph of that set of parametric equations. There's our plane curve. And you notice that as when we graphed it, we went from left to right on this graph. So as t increases, I go from here to here and up to here. So this graph looks like this plane curve. Kind of like this. And my orientation is left to right on this one. So there's my plane curve for that set of parametric equations. Everybody good with how we came up with these in our calculator? Now when you go to graph something else, make sure you switch back out of parametric mode. Otherwise you'll have a tough time. Graphing. All right. Let's look at how if we have a set of parametric equations, how we can figure out what the normal set of normal equation looks like. The y equals f of x equation. So we call that eliminating the parameter. So you want to turn a set of parametric equations into something that looks more familiar, something that we're more used to working with. So when we eliminate the parameter, the most basic way we do it, and we'll talk about another way to do it, the most basic way is we solve one equation for the parameter. We'll just call it for t. Solve one equation for t. And substitute that into the other equation. This isn't the only way that we eliminate the parameter, but it's the one that we'll use the most. So let's look at an example of eliminating the parameter. So let's say we have this set of parametric equations. X equals 1 over the square root of t, and y equals 2t squared. And we want to write our equation y equals f of x. Couple of things that we need to do when we eliminate the parameter. We need to look at the domain restrictions of our set of parametric equations. And we need to take those into account when we write our y equals f of x equation. So what would we have to restrict out of the domain for this set of parametric equations? What's that? T can't be negative. And one other thing, t can't be 0. So we're going to say t is greater than or equal to, or greater than 0. Greater than 0, can't be 0. Well, if t is greater than 0, what does that tell me about x? X is positive. So x is greater than 0. So when we write our equation y equals f of x, we're restricting our domain to say that x has to be greater than 0, because we have to say that t is greater than 0 for this part of our parametric equations to work. So when we write our final equation, we're going to say x is greater than 0. All right, we can solve either one of these for t. I'm going to work with the x equation, just that looks a little easier to me, but we can solve either one. So I'm going to write this. I'm going to multiply both sides by square root of t and then divide by x. So I get square root of t equals 1 over x. So t equals 1 over x squared. Square both sides. Substitute that into this equation. So y equals 2 times 1 over x squared squared. So y equals 2 over x to the 4th for x greater than 0. So if we didn't restrict the domain, we would look at this and say the only domain restriction I have here is x can't be 0. I can plug in a negative value for x and this is just fine. But for my original set of equations, t can't be negative, so I never get a negative x. Now let's take a look at what the graph of this set of parametric equations looks like. So let me go to the calculator. Clear out of there. So 1 divided by square root of t, and y equals 2 t squared. And we wanted to graph, we said that x has to be greater than 0, so I'm going to go from x, or from t equals 0 to t equals 10. And I'm going to go down here, and I'm going to do -5 there. I think that should work. So graph that, and there's my graph, there's my plane curve. Now if you notice when it graphed from right to left on this particular graph. So that would be my graph. Let's go back here. So my graph looks something like this. And my orientation for this graph is right to left. Because when t is very, very small, x is very, very, very large. Divided by a very, very small number, x is very, very large. But y is very small. So I'm over on this part of the graph. And as t gets larger, x gets smaller, and y gets larger. So I travel from right to left on this plane curve. So my orientation here is right to left. So this goes in the opposite direction that we're used to going. All right, we good? We're good with that example? So that's the main way they're going to eliminate the parameter. Solve one equation for t, substitute it into the other equation. Pretty easy process. We just have to remember to restrict the domain appropriately. Whatever our domain restriction is for t, we have to transfer that to our domain restriction for x for our new equation. All right, let's look at another kind of parametric equation. What if we had this set of parametric equations? X equals 4 cosine theta, y equals 4 sine theta, for 0 less than or equal to theta less than or equal to 2 pi. So this time our parameter is theta. We can think of our parameter as an angle. Looking at these equations, anybody have a guess on what the graph would be? What is it? Circular? What makes you think it's going to be circular? Okay, so we're thinking about the unit circle, and we know that on the unit circle, the x is the cosine of the angle, and the y is the sine of the angle. And as we move around the unit circle, as we increase our theta, we know we travel around the unit circle. What is a 4 going to be doing to this? We end up with a radius of 4. So we're going to guess this is a circle. Radius 4. So let's graph this in our calculator. So clear out of there. This is going to be 4 cosine t for my x and 4 sine t for my y, and my window, I'm going to go from 0 to 2 pi is about 6.3. And we'll graph that. Now it looks elliptical here because you can see on the x-axis my tick marks are a little further apart than they are on the y-axis. So I have 1, 2, 3, 4 units here, and 1, 2, 3, 4 units there. So if these were smaller, if these were compressed together, this would be a circle. Yes. Let's see. Are you in radian mode? Go to radian mode. Yep. Need to have make sure you're in radian mode. Or you're going to have a rad time, right? All right. So there's my graph. There's my graph of this particular set of parametric equations, my plane curve. What would you guess would happen if the number in front of the sine and the cosine were different? An ellipse. You'd have an ellipse. So it'd be stretched one way more than the other way. Let's look at how we eliminate the parameter for this set of parametric equations. When we see a sine and a cosine, when we think of the unit circle, what was our most used identity when we talked about trigonometry? What identity related sine and cosine? What's that? Tangent? Okay, so that was one. There was one that we used even more. Sine squared theta plus cosine squared theta equals 1. So whenever you see a sine and a cosine in a set of parametric equations, you should think Pythagorean identity. So to eliminate the parameter here, I'm going to square x. X squared equals 16 cosine squared theta. Y squared equals 16 sine squared theta. X squared plus y squared equals 16 cosine squared theta plus 16 sine squared theta. That equals 16. I'm going to factor that out. Cosine squared theta plus sine squared theta. Cosine squared theta plus sine squared theta is 1. And I get x squared plus y squared equals 16. Circle, radius 4, with the center 0, 0. So whenever you see a cosine and a sine, you think Pythagorean identity, and we end up squaring our x and our y to come up with our Pythagorean identity. And we did a problem earlier today in my calculus class where we were parameterizing an ellipse, and we did almost this exact same parameterization to parameterize an ellipse. And then if you wanted to parameterize a hyperbola, rather than sines and cosines, you would use secants and tangents, because secant squared theta minus tangent squared theta equals 1. So you end up with that minus sign in front of the one term, and you end up with hyperbolas. All right, so there are a couple of homework problems that end up having to do with trig functions. All right, last topic that we're going to talk about for today with parametric equations is finding parametric equations for a graph. This is really easy. So when we're finding parametric equations, what we're going to be given is our y equals f of x. So for example, and we're going to parameterize this two different ways. Y equals x squared plus 1. And we want to parameterize this by saying that x equals t. So they're giving us the parameter x equals t. All I need to do to find my other parametric equation, my partner for this one, is substitute this into the original equation. Y equals t squared plus 1. Substituting t for x, and this would be my set of parametric equations. If I wanted to parameterize the same curve, y equals x squared plus 1, and I wanted my parameter to be t equals x minus 2. Well, I'm going to say this tells me that x equals t plus 2, that's 1, and y equals, substitute this in for x, t plus 2 squared plus 1. I'm going to write this out. Y equals t squared plus 4t plus 4 plus 1. Simplify that. Y equals t squared plus 4t plus 5. So if I combine this one, x equals t plus 2, y equals t squared plus 4t plus 5, those would be my parametric equations for this equation in y equals f of x1. So two different parameterizations, two different sets of parametric equations for the same graph, y equals x squared plus 1. Both of these would give us this parabola. So finding parametric equations, when they give you the parameter, it's really easy. Sometimes you have to figure out, when you go further with this, you'll have to figure out what's going to be a good parameter. Here they just tell you the parameters. All right, questions there? So what we'll do next time after our test, we'll talk. So this won't be until next Monday, since we have a 4-day weekend. Next Tuesday, I guess. We will talk about polar coordinates, where a parameter is going to be an angle, and we end up getting our coordinates from an angle, and then we'll make graphs with polar coordinates, and then we'll talk about our conic sections using polar coordinates. Probably for our graphs, we would use our calculators. But in general, parametric equations, it's more important what you do with them than the graph, really. I guess I would say that. All right, our homework. Page 627. There we go.